Okay, so that's a correct solution. We know that x equals 8 is a solution. Can anybody, is there another solution? What do you think? Yeah. X equals 8 or x equals negative 8. Okay. How come? Well, because they both satisfy the original equation, right? Plugging in 8 or negative 8 in for x is going to give me an output of 8 because that's inside the absolute value bars. And remember, the job of absolute value bars, an absolute value function, only does one thing. If you input a positive, it doesn't do anything. If you input a negative, it makes it positive. So it multiplies by -1 to make it positive, right? That's its only job. What are some ways that we could maybe think about this? Well, one way is to think about it in terms of a distance on a number line. Okay, so the absolute value of x is like saying, what's the absolute size of this number? What's its distance from 0 on a number line? Okay, so if this is 0 and this is 8 and that's -8, the distance from 0 to each of those numbers is 8. So that's one way to think about what an absolute value does. It's talking about a distance from some center. We'll come back to this later on and talk a little bit more about this idea. Okay, but for now, let's just say that. Okay, if we think about what an absolute value graph looks like, and we're going to do some work with absolute value graphs here in the fairly near future, they just look like a V. Okay, it's a V with the vertex at the point 0, 0. This is a graph of P of x equals the absolute value of x. Notice the slope of the right leg of the V is 1. Slope of the left leg of the V is -1. Okay. I'll point this out to you because we're going to deal with this a lot in a couple of years in calculus. But the way we would define, there's another way we could define absolute value, and we'll come back to this soon. But another way we could do this anybody know what that means? Ever seen anything like that? It looks a little bizarre, doesn't it? Raise your hand if you've ever seen anything like that. Maybe I'm seeing some, possibly. Raise your hand if you know you've never seen anything remotely like that before. Okay, most hands go up. That's okay, that's fine. This is called a piecewise function. We'll talk about these in this class pretty soon. Maybe I won't spend a lot of time on that now because you guys have never seen it before. We'll come back to it. Remind me, I'm sure I'll remember this, but when we talk about piecewise functions here, within the next month or so sometime, remind me to talk about absolute value functions if I forget. I won't forget, but just in case. But I'll skip that for now. Okay, so what about something like this then? How do we solve this equation? We solve this equation. Let's talk about this. There's a couple tricks I want you to remember algebraically. I want to look ahead at one thing real quick. Hang on. I want to just make sure I got. There it is. Good. Okay. Yeah, perfect. Okay. So I'm going to relate the way we solve this to the graph of an absolute value function in just a second. But first, let's just talk about kind of the nuts and bolts of what's our process look like. When I want to solve an absolute value equation, the first part of the process is you want to isolate the absolute value. Okay, so that means we're not going to touch anything inside the absolute value function. In fact, I'm not even going to tell you what's in there for now. It's irrelevant. I'll give you a sneak peek. Oops. Oh, it's frozen. There's a sneak peek at what's in there, but we don't care. We can't touch that anyway, right? When we're solving an absolute value expression, that's off limits completely. The first step is we want to isolate the absolute value. So let's treat this, at least in our mind, you're always going to treat that as just, we'll call it hand. Okay, it's something that's off limits. It's covering something up. So if I have 4 times hand minus 2, what would you do to solve for hand, to isolate hand? in order? What are the two steps? But what you got to do first, if I want to isolate what's behind my hand, got to use inverse operations. What are you going to do first? Pretend that's a big X. If I had 4x minus 2 equals 38, how would you solve for x? Oh, got to add 2. There you go. Maybe I didn't hear that. Did you guys say that first? Oh, it's just my bad hearing, I guess. So we're going to add 2, and then divide by 4. That's probably what you said, and I just missed it all. Okay, so we add 2 to both sides. We get that. We divide by 4, and we get that, right? So now we know that the absolute value of hand is equal to 10. So what are the two possible values for what's behind my hand? If the absolute value of that is 10, okay, it could be 10 or it could be negative 10, right? So then all I've got to do now, once I get to here, is whatever is inside the absolute value, we still don't know. It either equals negative 10 or, and this, by the way, is my symbol, in case you haven't seen this or don't remember it. That V-looking symbol means or in math, okay? So either what's inside the absolute value, call it the argument of the absolute value, is equal to 10, or it's equal to positive 10, okay? I called it U, again, because I'm going to have all you guys in calculus here in a couple of years, and this is what we'll come to call a U-substitution in calculus. We want to substitute an expression for a variable. Usually we choose U. So in this case, the U is equal to negative 2x minus 6. But we didn't even need to know that until we get down to this final step down here. Once we've isolated the absolute value, whatever's inside is set equal to the number outside or its negative opposite. And then we just solve for both of those two little results, those two little equations that we get when we set the argument equal to the positive number and the negative number and get our two outcomes. So what happens here? So we get here, I'm going to just get rid of that. So in both cases, I'm just going to add 6 first, correct? And then divide by negative 2. So that's going to give me negative 4 here when I add 6. Divided by negative 2 gives me positive 2 as an outcome, okay? On the other equation, I'm going to add 6 to 10 and get 16. Divided by negative 2 is negative 8. So my two possible answers are 2 or negative 8, okay? How would I know if I got it right on a test? Check it, plug them in, right? Plug them in and see that they evaluate the original statement. So if we try those, what were they, 2 and negative 8? Let's just try them, just kind of walk through it in our heads. If I plug 2 in, 2 times negative 2 is negative 4, minus 6 is negative 10. Absolute value of negative 10 is 10, times 4 is 40, minus 2 is 38, check, right? What about 8? Negative 2 times 8 is, hang on, was it 8 or was it, what were my two results? Can't remember. Negative 8 or 2, so negative 8. Negative 2 times negative 8 is 16, minus 6 is 10. Absolute value of 10 is 10, and that's right where we, same path we followed last time, right? So we know we're getting the same result. So they work, okay? Both of those work. Okay, why is this so? How can we visualize this? Well, let's look at our function again. Okay, here's our absolute value function. Let's say that we're solving the absolute value equation. The absolute value of U is equal to A, okay? U is whatever's inside there, right? Well, if I graph this function, and here's the function f, or I'll just make it y. Y equals the absolute value of U. There's my V shape, right? Just like we got before, only U instead of X this time. I want to know when the absolute value of U is equal to A, that's going to be when its Y value is A, correct? Okay, so one way to think about this is we could just intersect the graph of the red U-shaped graph, the absolute value function graph, with the graph of y equals a, and I get two intersections. I get an intersection there and an intersection there. Okay? Remember doing stuff like this in Algebra 1? If I want to, you can solve, and this is a great trick to use technology to solve equations. If I have some expression equal to another expression in an equation, I can do this like in Desmos, for example, or on a graphing calculator, by graphing y equals the left side, whatever the left expression is, and y equals the right side, and then by finding the intersections, I'm finding the x values where that's happening. Okay? Remember doing that stuff? I'm sure you do. It'll come back to you. We'll get some practice with it. Well, look where those are happening. Those are happening at the points over A and up A, right? Because the slope of this line is 1, isn't it? So if the y value is going to be A, then I had to go over A to go up A, right? If the slope is 1. Back over here, the slope is -1. So if the y value is A, I had to go backwards by A to go up by A, right? So the main thing we're looking at here, the important part of this, is that. So I end up with these two results. The intersections occur here and here. And look what that looks like then. On a number line, the absolute value of u is equal to a for the x values at a or -a, right? So here's our little procedure that we're always going to use. This is the little formula, if you will, that tells us how to solve an absolute value equation. We isolate the absolute value, and whatever's inside is either equal to the positive or the negative of the outside number. Okay, give me thumbs on that. How we doing? Okay, up, down, sideways. Could be a little shaky up, maybe so. Okay, good. Let's try some practice. So how about this one then? Here's my equation that we're going to solve. 2 times the absolute value of 2x minus 20 plus 11 equals 79. What's my first step? Say it again. Subtract 11 and what am I doing by those 2 steps? What would I call that? What am I trying to do here? What am I accomplishing by? Okay, good. I'm isolating the absolute value. So I don't even care what's inside it, right? Remember, that's my first step, is to isolate the absolute value. Okay? All right. So we're going to subtract 11. So I get 2 times the absolute value function equals 79 minus 11, which is 68, right? Divide by 2, you told me. That's correct. So those guys cancel. And then I get my isolated absolute value equals 34. Good? Okay, well now we can look inside. What's inside? Okay, well, turns out what's inside is a 2x minus 20. We'll do something else too. I'm gonna make that yellow. Okay, we isolated the absolute value. Now what can you tell me? Remember, I'm going to trade my, in essence, I'm trading my single absolute value equation for 2 non-absolute value equations. That's the trade we're always going to make. When we get to inequalities here in a couple lessons, we'll do the same thing. We'll have an absolute value inequality that we're going to trade for 2 regular absolute values with no inequalities in the form of a compound inequality. That's later, right? Again, we're trading the absolute value equation for 2 regular equations. What are they? Here. Okay, one of them is 2x plus 20 equals 34. Did that just get like really weird looking and bright? Doesn't that look different? I wonder if my bulb's about to go out. It could be. Yeah, that looks really strange. or and I'll just solve both of those, right? No big deal. Okay, and I want to point one other thing out too. If I go back to this previous example, okay, there's a tendency for people to want to do this. They want to say, okay, well, the absolute value of negative 2x minus 6 is 2x plus 6. How come? The people want to do that probably because absolute values undo negatives, right? Everybody agree? That's not what we do though, right? Because that would have changed my results. What we're asking the math gods here is, by doing this, solving this equation, we're asking the math gods, what value of x could we plug into this equation and get that result, right? It's a different equation if I write down 4 times the absolute value of 2x plus 6. That's going to give me different results that would be incorrect. Okay, so we don't just get rid of negative signs attached to variables, for example, or if I have an expression involving a variable, I don't get to just say the absolute value does away with the negative signs. Okay, see what I'm saying? Give me thumbs on that idea. Okay, good. How about that one? What do I have to do there? Multiply by 3 to isolate the absolute value. Okay, if I multiply by 3, I get the absolute value of whatever's inside is equal to 156. Well, what's inside? What's inside is a 4x minus 20. So what are my two equations going to be? What are the two equations I'm going to come up with here? Okay, not quite, right? Because the absolute value of u is equal to 156 when either u is equal to 156 or u is equal to negative 156, right? See what I'm saying? So we're going to make this split here, this bifurcation in this process, where we're going to go from one absolute value equation down to two regular equations. There's two ways that the absolute value of hand can equal 156. Well, hand could equal 156, or hand could equal negative 156, right? In both cases, the absolute value is going to make it positive when I plug a value of x in, right? So again, here's my recipe. It's right here. If I isolate the absolute value, if an isolated absolute value is equal to some number, call it a, then whatever's inside either equals positive a or it equals negative a. Okay? So I got two equations to solve, and I could do that. I'm going to get two different results. We don't even have to finish. Right? I'm going to get two different answers, though. Okay? How about that one? First step. Add 11. Because I'm trying to isolate the absolute value. So I'm going to add 11 and then what? Divide by 2. Okay? So if we do that. I get 2 times the absolute value of something is equal to 0. Divide by 2, and that's okay to do, right? What's 0 divided by 2? 0. Yeah, it works. And so now I get the absolute value of something is equal to 0. Well, let's look inside. Inside, we have a 3x plus 6. So what's my rule then? What are the two equations I'm going to get? Kind of weird, right? If this were a 10, what would they be? Okay, yeah, 3x plus 6 could either equal 10 or it could equal negative 10, right? Problem here is that 0 is neither positive nor negative, right? It's the boundary between the two. So really, I'm getting the equations 3x plus 6 equals 0 or 3x plus 6 equals 0. I only get one equation out of it. That's okay. There must just be one solution this time. Subtract 6 and divide by 3, and what am I going to get? Negative 2. Everybody agree? I can check it. It's going to work. 3. So if I plug in negative 2, I get 3 times negative 2 is negative 6 plus 6 is 0. The absolute value of 0 is 0. 2 times 0 is 0. 0 minus 11 equals negative 11. It works. Okay, now what must this have corresponded to in terms of this picture we drew a while ago with the v? When we isolated the absolute value, if we got a positive answer, well, then there's going to be two places where the absolute value has that positive y value. But this time when we isolated the absolute value, what was it equal to? In that last example? 0, right? Well, look at my absolute value function. It has a y value of 0 at the vertex. There's only one place where that happens, so we only got one solution. Are we good with that? That can happen, right? Okay. How about this one? Steps to get the absolute value by itself. Add 1 and then divide by 3. Okay, good. I like it. So those guys cancel. I get 3 times my absolute value equals negative 6. I divide through both sides by 3. And I get the absolute value of something is equal to negative 2. What's inside? 2x minus 1. So what are my two equations going to be this time? Or do you see a problem? Would I use 2x minus 1 equals negative 2 and positive 2 because it's the opposite? Does that seem reasonable? We could try it, but see if it's not correct. At least if you can tell me why. So we'll go down this rabbit hole and then you tell me why this was a mistake. If I do this, I get 2x minus 1 equals negative 2 or 2x minus 1 equals positive 2. Okay, so if I solve this one, I add 1 and I get negative 1 divided by 2. I get x equals negative 1/2, or how about over here? I add 1 and I get 3 divided by 2. X equals 3/2. Well, it looks like it worked. Let's try it out and see. If I go back to my original equation, though, and here it is. Let's see if I can make a copy of that. Yeah, I can. So there's my original equation, right? Yeah, my absolute value equation. We got results negative 1/2 or 3/2. Let's try negative 1/2. If I plug that in, 2 times negative 1/2 is negative 1, minus 1 is negative 2. Absolute value of negative 2 is 2. 3 times 2 is 6. 6 minus 1 is 5. Ooh, I get the result 5 equals negative 7. That's not true. So that's a false solution. Okay, well, let's try the other one. What about the other one? It was x equals 3 halves. If I plug that in, 2 times 3 halves is 3, minus 1 is 2. The absolute value of 2 is 2. Well, that's going to give me the same outcome, isn't it? Because I got 2 out of my absolute value expression last time. So that also gives me the false statement, 5 equals negative 7. That's, once again, that's not true. And so that's not a solution. Where did we go wrong? This step right here must have been a mistake. How come? What do we see about that allows us to say, no, we're done. This can't work in this equation right here? Something about that doesn't make sense. What do you think? There you go. The output of an absolute value could never be negative, could it? The absolute value output either always has to be positive or 0. It could be 0. The absolute value of 0 is 0. But the absolute value of no number, there's no possible number I could input and get an absolute value that's equal to negative 2, right? So we see right here, because of this negative sign, this is impossible. And so there's no solution. If we go back to this picture, it'll make sense. Look at our absolute value graph. If I have the absolute value of u is equal to a negative number, well, y equals a negative number is a line down here. That's never going to intersect the red graph, is it? So there's no solutions. Okay? All right. One more. How about this one? Okay, this looks harder and different because I've got an absolute value expression equal to an answer involving a variable. I'm going to go ahead and just unveil what's behind there. We know that we can't touch the anything inside the absolute value until it's isolated, but it is isolated, right? So what's my rule that I follow when I get an isolated absolute value is equal to something? What rule did I follow with numbers to set up my two equations? What did we do? What did we do back here? Okay, it either equals whatever's outside the absolute value bars or it equals its opposite, right? Okay, well, let's apply that. So here then, whatever's in the green, whichever's inside the absolute value bars, which is my green, we'll kind of color code this a little bit. The green expression, so 12x minus 14, either has to equal the positive, so 14x plus 4, or what's inside has to equal the opposite of what's outside. So negative the quantity, 14x plus 4, right? We'll just solve both of those and see what we get, okay? So here I'm going to push the x's in which direction? We're going to solve this equation. Left or right? Right, good. So we're going to push these guys over here. So I'm going to subtract 12x. So those cancel, and I end up with negative 14 equals negative 14x minus 12, or 14x minus 12x is 2x. We about out of time? Okay, see, oh man, how much time we got? Like 1 minute? Ah, darn it. Okay, we'll wrap this up tomorrow, and then I'll let you guys work tomorrow on it.